I'd like to thank the organizers for giving me this opportunity. And so this work is done in collaboration with my student Sudeshna Sen, and it's under review. So it's about a model that we are suggesting can show quantum critical Mott transitions. So let me explain for the students what I mean by quantum critical Mott transitions. The Mott transition itself is a metal to insulator transition driven by interactions. That's the simplest statement that can describe Mott transitions. And a quantum critical transition is one that takes place at t equal to 0, driven by an athermal parameter, and it occurs due to quantum fluctuations, not due to thermal fluctuation. So this work describes the results of or the physics of a model system that can that exhibits quantum critical Mott transitions, which means at t equal to 0, metal insulator transitions driven purely by quantum fluctuations. So in real experiments, Mott transitions have been observed to be of generally two classes. One is the one that is shown here in V2O3, vanadium oxide, which is a first order transition. As you can see from here, these are the two spinodal lines, and this is the coexistence regime, or the regime where the hysteresis occurs in the temperature pressure plane. And the system goes from a Mott insulator to strongly correlated metal as a function of pressure. And as you drive the pressure, you can see hysteresis in resistivity, for example. And the theoretical framework for this kind of system is a multi-orbital Hubbard model. And one can study this model using dynamical mean field theory and its cluster extension. The other class of Mott transition has been observed in this organic salt, where you see that the Mott transition seems to be occurring purely at t equal to 0, again as a function of pressure and temperature. And although I have shown only one representative example of these two classes, it turns out that most Mott transitions in reality are of the first type, where you see first order Mott transitions which end in a second order critical point at finite temperature. And these are really rare, and the only other known example is that of a bilayer helium system, where there is a layer selective Mott transition that takes place. And the theoretical framework for this is not yet completely known. There are some proposals, but there is no consensus yet. Okay, so we are basically motivated by this physics of the quantum critical Mott transition, and we are proposing a model which seems to be exhibiting this a whole surface of quantum critical Mott transitions. And let me just explain this model, because that's one of the main results of our work. So think of three different layers where there is a square lattice on each layer. The first layer, the top layer, has, let's say, local moments sitting in the lattice without communicating with each other. The second layer is a pure metal. It's non-interacting electrons sitting on moving on a lattice. And the third layer is also non-interacting electrons moving in the lattice. And the first two layers are coupled by an intra-unit cell hybridization. And together they are known as the periodic Anderson model. So the local moments are not allowed to hop in the first layer. In the second layer, the conduction electrons can move around. And the third layer and the second layer are coupled via an inter-layer coupling. Okay? So the conduction electrons can tunnel into each other. So the second layer and third layer are coupled like that. So this is basically a Kondo insulator metal model system, because the first two layers, or the dark brown system that you're seeing here, is that of a Kondo insulator, which is basically the symmetric limit of a periodic Anderson model. So what I mean by that is that if you decouple these two layers, the first layer would just behave like a renormalized band insulator. And if you couple these two layers, it turns out that the local moments that were not hopping from one side to the other side acquire a renormalized hopping and are able to hop around, and thus the F electron system in this Kondo insulator also becomes metallic. Now the possibility arises that if you turn on interactions, or if you increase the interactions beyond a certain limit, you could observe a Mott transition in this F electron system, which ordinarily, if you had decoupled these two layers, would not occur. So what I mean by that is that if the interlayer hopping were to be turned off, then this Kondo insulator never actually becomes a metal. So the gap always remains, and the gap is actually the low energy scale in the system. So that's the question. And then in second quantized notation, we can write it in the following form, that there are, it's basically a 3 electron species system where there is a intra-layer hopping in all the 3 layers, in the 2 layers, sorry. There is a hybridization between the local moments and the conduction electrons on the first layer. And there is orbital energies for the electrons. There is orbital energies for the F electrons. The interaction is present only on the local moments. And there is an interlayer hopping which allows the electron from the first layer and the second layer to hop onto each other. And the framework that we use to solve this model is called dynamical mean field theory. And without going into details, the main thing about the dynamical mean field theory is that it takes a lattice model and maps it onto a single site problem, but that single site problem is sitting in a bath that is self-consistently determined. So one can write this down formally as basically integrating out all the degrees of freedom of the lattice except one, and then a dynamical field is generated which has to be determined self-consistently. And so let me begin by showing you the results. So the spectral function is basically found out through the imaginary part of the Green's function, and it denotes the density of states. And what you see here is the conduction electron density of states as a function of frequency. And there are 2 curves here. One is a T perpendicular of 0.2 and a 0.7. If the T perpendicular were to be 0 exactly, which means that the layers were decoupled, this gap would have been a hard gap. The Kondo insulator would have a hard gap. However, by turning on this interlayer coupling, it turns out that the gap becomes soft, it becomes quadratic. And I'm not showing you the F electron density of states, but the F electrons actually become gapless. And so if we take the F electron density of states and then plot it as a function of a scaled variable, so omega t perp squared over zv squared, where z is the quasi-particle weight derived from the self energy, then what you see is that there is a universal collapse for different u values. And what you see in the inset is that if you don't scale it, then you see that there is an exponential narrowing of this Kondo resonance. So this is again saying that before the Mott transition, the system is actually a Fermi liquid because there is adiabatic continuity to the non-interacting limit. And surprisingly, what we find is that by increasing this interlayer coupling, which would normally expect that if you increase the interlayer coupling, you're making the electrons more itinerant, what really happens is that there is again a narrowing of this resonance, which means that the scale again decreases exponentially. And then beyond a certain U critical and beyond a certain T perpendicular critical, a gap opens up in all the 3 layers, in the density of states of all the 3 layers, and what we get is a Mott transition. And the question then is, what is the order of the transition? Is it second order or continuous? And to understand that, what we look at is the low energy scale on the Fermi liquid side and the Mott gap on the Mott insulating side. And all our numerics suggest that the scale, the Fermi liquid scale as well as the Mott gap, both vanish at exactly the same critical point. And we can do this as a function of u as well as T perpendicular as well as the hybridization. And we find that there is in fact a whole surface of quantum critical points which separates a Mott insulator and a Fermi liquid phase. So in fact we can do certain analytics as well, and we can show that the U critical in fact depends on the T perpendicular squared as 1 over T perp squared, and it is directly proportional to the square of the hybridization. So that is actually borne out by the numerics as well. And there are certain similarities and differences with related models. So if we consider, for example, the single band Hubbard model, which is the paradigm for the Mott transition, then that shows a first order Mott transition. If we look at our model, that shows a second order Mott transition, that shows continuous T equal to 0 Mott transition. Whereas if we consider a pure Anderson lattice, where there is no metallic layer to couple to, then you can see a Mott transition only when there is a next nearest neighbor hybridization or a nearest neighbor hybridization. So in this sense, this model seems to be showing quite new physics, which has not been seen before. And we have to still verify a lot of things. We have to find out the universality class. I mean, the first order Mott transition is known to be in the Ising universality class, whereas we don't know what the universality class of this model is. We have to look at scaling and exponents, and we also want to look at finite temperatures. And we are suggesting to the experimentalists that these things can actually be fabricated now. So layered heavy fermion systems are a possibility these days. So one can look at uniaxial pressure and then try to mimic the increase in interlayer hopping. So, and it seems that it is possible. So yeah, that's all I have to say. Thank you.
Let's thank the speaker and time for questions.
That's basically the 1 over z, and 1 over z goes to 0. So, and we know that it goes to 0 as power loss, and the exponents are actually dependent on t perpendicular u and v. So where you are in the phase space, it depends on those, but they are not the critical exponents.
Okay. If there are no further